Hello students, today we are going to discuss the last application of Gauss theorem, that means how to find the electric field intensity due to a uniformly charged spherical shell. Imagine a spherical shell which contains positive charge. The positive charge will only lie on the surface of the shell. Inside the shell, electric field is 0, electric charge is also 0. I want to find the electric field at any point P which is marked outside the shell. So electric field, first we are going to find electric field outside the shell. So what we have to do is imagine a spherical Gaussian surface which is marked as dotted green circle. So imagine that as a sphere which includes our spherical shell. Now you take a small space ds on that sphere and you can see that area vector and electric field both are in the same direction. So theta is equal to 0. Applying Gauss theorem, phi is equal to surface integral E dot ds equal to q by epsilon 0. Since E and ds are in the same direction, theta equal to 0, cos 0 is 1. Therefore, the equation can be written as integral E ds equal to q by epsilon 0. E ds cos theta, but cos theta is 1 because theta is 0. So we will write integral E ds equal to q by epsilon 0. E is constant, so we take the constant E outside. So E into integral ds equal to q by epsilon 0. Now, integral ds means the entire surface area of the Gaussian surface. Surface area of the sphere. Gaussian surface is a sphere here. So surface area of the Gaussian surface. So E is equal to, phi equal to E into 4 pi r square, which is q by epsilon 0. So from that equation, I can find E as q by 4 pi epsilon 0 r square. This equation, that means E is equal to q by 4 pi epsilon 0 r square. This is same as the electric field due to a point charge. What does that mean? It means that electric field due to a uniformly charged spherical shell at a point outside the shell is such that if the whole charge were concentrated at the center of the shell. That means imagine the entire charge of the shell is concentrated at the center of the shell as a point charge, and we can use the equation q by 4 pi epsilon 0 r square. Now we already know q is equal to sigma into a. A is surface area. So we will take surface area of the shell. Radius of the shell is capital R. So q can be written as sigma into 4 pi capital R square. Putting that finding in the above equation, so we will get E is equal to sigma into 4 pi r square divided by 4 pi epsilon 0 small r square. So 4 pi and 4 pi get cancelled. Finally, you will get E is equal to sigma by epsilon 0 capital R square by small r square. Now, let us see how to find electric field intensity at any point on the surface of the shell. So just mark the point A which is on the surface of the shell and imagine a Gaussian surface. Here Gaussian surface and the shell is having the same radius, that is capital R. Therefore, in the above derivation what we studied, instead of small letter r, we can just substitute capital letter R, because since we are finding the electric field on the surface of the shell, Gaussian surface and the shell has the same radius. Therefore, E into ds equal to q by epsilon 0. Instead of integral ds, I will put E into 4 pi capital R square. In the previous derivation, it was small r square. I substituted small r square with capital R square. Therefore, finally, we get the equation as E is equal to q by 4 pi epsilon 0 capital R square. Now, q can be written as sigma into capital A, and A is again 4 pi capital R square. Therefore, q is equal to sigma into 4 pi R square. Putting this in the above equation, therefore we will get E equal to sigma into 4 pi R square by 4 pi epsilon 0 R square. So 4 pi epsilon 0, 4 pi so 4 pi R square and 4 pi R square get cancelled. The remaining thing is sigma by epsilon 0. Therefore, we will get E equal to sigma by epsilon 0. Now the third one, at any point B inside the shell. I already told in the beginning that inside the shell there will not be any charge. Charge inside the shell is 0. Therefore, we don't have to do the derivation. We already know the answer. E is equal to q by 4 pi epsilon 0 R square. And since q is equal to 0 inside the shell, you can just substitute 0 instead of q. So 0 by anything, 0. Therefore, E is equal to 0 inside the shell. Okay. So when I draw the graph connecting the distance and the electric field inside the shell is 0. So we don't have to draw any graph there. And on the surface of the shell, that is, I marked capital R, that is the radius of the shell. On the surface of the shell, electric field is maximum, and from the surface to any point outside, electric field varies as 1 by R square. That is why the graph is having a curved shape. With this, our first chapter comes to an end.